Welcome to Knowledge is Power Educational Videos. This is the Engineering Problem Solving series. This will be Lecture 2, Part 1. In this lecture, we're just going to do a general math refresher. What we're going to get into in the next part of this lecture, which will be a separate video, is going to require some foundation in mathematics. And if you're anything like me, and you're going into to these types of courses later in life, you've probably been removed from general ed for quite some time. So we just want to do a quick refresher on fractions and exponents and make sure that we understand what's going on. Now, if you've already got a pretty good root in fractions and exponents, then skip this video. You don't have to watch this. Just go ahead and go to the next one. And for those of you that are going to watch it, I know you might remember most of this, and that's fine. And that's definitely a plus if you do. But we're going to be breaking these things down to try to help people understand them. If somebody comes in here and they're very unfamiliar, I want them to come out of this video understanding everything that we talk about as far as fractions are concerned, as far as exponents are concerned. So we're going to be breaking it down to a pretty base level and explaining things, a little bit over explaining, if you will, to make sure that everybody comes out of this with the knowledge that they need to move on in the series. So we're just going to call this the math refresher. Let's get the pen turned on. Let's get over here. Okay. This is the math refresh. So we're going to start off with fractions. Now, you all remember a fraction would look something like this. 5/4. Right? And that's simple enough. Now, things that we need to remember is that this top part here, that's your numerator. Actually, let me check the spelling on that. I want to make sure that I don't. Let's see. Yeah, that's good. And I don't want to misspell things, make myself look stupid here. And the bottom portion is going to be the denominator. Numerator and denominator. So, and what we're going to be doing moving forward in this course is we're going to be dealing with the manipulation of fractions. And when we see a fraction in this course, you're gonna think of this fraction as just any other fraction, really. But we use units in this course. We're going to use units in there as well. So the units have to be considered. So for instance, if we do 9.8 meters per second squared, you can imagine this as 9.8 meters over second squared. These things are going to come into play when we get into the fundamental dimensions here in this next part. But we got to understand right now that what we're looking at is essentially a fraction. So the first thing we know about fractions is addition and subtraction. So if we have 2/3 plus or minus, doesn't matter, 3/6. If you remember your fractions, you're going to remember that we have to have, in order to do addition, and only addition, right, we have to have a common denominator. Again, I'm sorry about my sloppy handwriting. I'm doing the best I can, guys. So in this situation, we have to have a common denominator. We have to have this bottom half of our fraction needs to be the same number. And this applies to units as well. If we're doing it with units, we can't take this and add something that's meters over minutes to it. We need to get that minutes set over to subtraction in order to be able to, or to, I'm sorry, to subtraction, over to seconds to be able to add it, right? So here we have 2/3 plus 3/6. How do we get that common denominator? We're going to take this 2/3. We're going to multiply. In order to get the bottom to 6, we're going to need to multiply that 3 times a 2. But anytime we do something to the denominator, we must do it to the numerator. So we're going to take 2/2. We're just going to multiply across. 2 times 2 is 4, right? 2 times 3 is 6. Now we can add our 3/6. And when we add, we don't add the denominator, okay? We're only going to add across, and this is going to equal 7/6. And the reason is that we don't add that denominator is if we imagine that we have a pizza. Let's just chop it up into a pizza here. We're going to draw a little pizza. And this thing is cut 6 ways. So we're going to do one way, 4 way, 6 ways. Okay? And over here we have 4 out of 6 slices. So we're going to color in, change, matter of fact, let me go ahead and draw another pizza here. And we're going to draw another pizza here. One more time. This is real sloppy, I know, guys, but just hang in there with me. Like I said, I know that some of you guys are already familiar with this and you're thinking, come on, Randy, get to the meat, man. We're tired of this. But not everybody is, man. I want everybody to come out of this knowing what's up. So here on our 4 out of 6, we have 4 slices of our pizza. On our 3 out of 6, we have 3 slices of our pizza. And then these over here, these don't exist. These slices are empty. If we were to add these 2 pizzas together, not only are we going to have this whole pie, right? Because we have 6 slices in total for a pizza. Here we have 4 slices of pizza. Here we have 3. That gives us 7 slices. So not only are we going to have all 6 of these slices, but we're going to have 1 slice on the side. We're going to have 7 out of 6 slices in our pizza. And that makes sense. Now, if we try to add straight across, or if we try to add the denominator as well, we would end up with 7 out of 12 slices, and that wouldn't make much sense because obviously we can see from our pizza example here, it just simply doesn't. Now, let's talk about multiplication and division. And the key thing here is that multiplication and division go hand in hand as far as fractions are concerned. And as you can see of what we did in this example right here, when we have 2 fractions, let's say we have 2/3, and we want to multiply this by 3/6, we simply multiply straight across. We get 6 over 18. Now, I know you might be confused by that, but I challenge you to do the pizza example, to come up with a way to do the pizza example, but you have to remember that anytime we do a multiplication, let's say we're doing 2 times 3, what we essentially have, right, what we essentially have is we have the number 3 2 times. These two are equivalent. These 2 things here are equivalent. And the same as also if we have the number 2 3 times. These are also equivalent. Okay? So what we have in this situation is we have the number 2/3 3/6, 1/2, right? Because 3 over 6 is equivalent to 1/2, right? So we have 2 over 3, 1/2 of the time. 1/2 times, which would equal 6/18. And that to go into the proof of this would take too long, and it could seem confusing, but it's really not. And if you sit down and you just work through it one time for yourself, you're going to find, okay, this all makes sense now. If you're anything like me, when I'm confused by something in mathematics and I work through it, the moment I break through and I get it and I make that proof happen, it then completely, totally makes sense, and there's no more questions left. So what about division, Randy? What about division? Let's talk about division. So let's say we have, matter of fact, let's say something here. I want to point out something to you guys. The number 2, just by itself, is equivalent to 2 over 1. Because essentially what we're saying is 2 divided by 1, right? Right here we're saying 2 divided by 3, and 3 divided by 6. So 2 is equal to 2 over 1. Therefore, when we look at a fraction like 2 over 3 divided by a number, 2, that's the equivalent of saying it's divided by 2 over 1. Okay? And that makes perfect sense. It's the equivalent of saying that it's 2 over 1. Now, in the case of this division, we could simply say that 2 over 3 divided by 2, and then anytime you see a whole number in the bottom, we say it magically floats up. It magically floats up, and that's because when we do fractional division, when we do like 2 over 3 divided by 4 over 5, the way that we look at that is actually by taking the reciprocal of this bottom number and multiplying it by this top number. Take the denominator's reciprocal and we multiply it by the numerator. So we have 2 over 3 times, and the reciprocal is just this flipped, 5 over 4. Okay? And that brings us to 10 over 12. Now, this right here, back to our other example, this one right here, our 2 over 3, I'm going to write it again over here, 2 over 3 divided by 2 is equivalent to 2 over 3 over 2 over 1, which is equivalent to 2 over 3. We're going to multiply by the reciprocal times 1/2, which gives us 2 over 3. I'm sorry, let me bring that back. Ooh, not 2 over 3. 2 over 6. Now, I said just a minute ago, and I don't know if you guys paid attention, but I said we normally say in math that this floats up. It just floats. We call it magic. So if we look at a number, 2 over 3 over 2, and we have a whole number on the bottom, we basically could say that is equivalent to 2 over 3, and it floats up times 2. Put some parentheses around that, which is, again, 2 over 6. These are equivalent. So the key here is we're just gonna make some notes here off to the side. I'm gonna do it in a different color. Give us a blue. We're gonna say notes for add and subtract common for mult. Actually, we're not even going to do an and on this. We're just going to take that away. For mult, we multiply, oops, go back to my pen. Multiply across. And for division, we multiply by reciprocal. Oh, I don't even know if that's spelled right. Oh, Lord. You know what it means, though. We're not going to go into that. I don't do grammar. I do math and computer science. So, anyways. So, for addition and subtraction, we common denominators, right? We have to find the common denominator by multiplying one of them into something. And sometimes, just so you guys know, sometimes we're going to deal with denominators that don't really line up well. Like, for instance, let's just do another example. Do another example right up here. We'll say that we have 3/5 plus 3/3. That's sloppy. Take that back and do it one more time. 3/5 plus 3/3. In this situation, we can't really multiply these by anything to meet a common denominator unless we do them both. So in this situation, we got to take this 3/5 and we got to multiply it by 3 over 3. And then over here for this 3/3, we got to multiply it by 5 over 5, which results in 9 over 15 plus 9 over 15. Oh, what am I doing? Plus 15 over 15. I'm sorry, guys. 15 over 15. Now we could come to our solution of 24 over 15 by adding. So sometimes you're going to have to do a common denominator on both sides. Now multiplication, we just multiply across. Doesn't matter what it is. We'll do another example over here. And we'll say that 5 over 5 times 10 over 10. You just multiply across. That's 50 over 50 because 5 times 10 is 50. 5 times 10 is 50. Same with 2 over 3 times 5 over 10. 2 times 5 is 10. 3 times 10, 30. Easy, right? And then last but not least, for division, we multiply by the denominator's reciprocal to do the division. We'll do one more example over here. We'll say, we'll do this one right here, 2 over 3 divided by 5 over 10. You know what, matter of fact, just to make it interesting, 2 over 3 divided by 10 over 5, which equals 2 over 3 times 5 over 10, which comes to the same solution as above, 10 over 30. And that's pretty much fractions. That's the 3 ways we're going to work fractions. Is what you need to remember. Now, our next section, our next little part we're going to talk about is exponents. Now, you guys remember our scientific notation from the last lecture, 1 times 10 to the third, things of that nature, but a lot of people have forgotten the rules of these exponents. So we're going to do a quick refresher on the rules of exponents and how they work. So first thing first, what is an exponent and how does it work? An exponent, if we say 10 to the 3, essentially what we're saying is we're multiplying 10 by itself 3 times. That's all. If you do the math on that, you're going to notice that it comes to 1,000. So if we have 2 to the 4, what we're saying is 2 times 2 times 2 times 2. 2, 1, 2, 3, 4 times, which is going to be equal to 16. So on and so forth. That's how exponents work. That's what the notation is telling us to do. It's multiply that number by itself however many times we have up in that exponent. Now let's talk about the exponent rules. And this, we're going to talk about, first things first, we're going to talk about the power rule. Okay? This is written as a to the m, all of that to the n is equal a to the n. Now, this may seem a little complicated, but we're going to put it, what are these letters that you're throwing in here and all that, Randy? You're confusing me. Just calm down. We're going to put it into a notation like this up here or this right here, and maybe it'll make more sense. So let's say we're dealing with 2 to the 2. But we're taking that, you guys remember your rules, your PEMDAS, but we're taking this and we're raising it as well. We're doing this as a whole nother exponent to the 2 again. So we're doing 2 to the 2 and then raised to the 2 power. So let's work this out. Let's work this out the old style. Let's just look at this in PEMDAS, right? So we know that we're going to start in our parentheses, and then we're going to go to exponents, right? So what is 2 to the 2? From up here, what we learned that 2 to the 2 is just 2 multiplied by itself 2 times. And then if we raise this to the 2, what is that? Well, that's like saying 2 to the 2 times 2 to the 2. And what does this come out to? What does this come out to? 2 to the 2 comes out to 4. And 2 times 2 comes out to 4. Right? And what is 4 times 4? That comes out to 16. That's interesting. Right? That's interesting. Our 16 here, that's the same as what we got up here for 2 to the 4. Let's look at our rule again. We say that a to the m raised to the n is equal to a to the m times n. So in this situation, we have 2 to the 2 raised to the 2. What is that equal to? 2 to the 2 raised to the 2 is equal to 2 to the 2 times 2. Right? A to the m times n is here. And then a to the mn, that version is there. And what does that go to? That goes 2 times 2 is what? We just did it over here. It's 4. 2 to the 4. And where did we see 2 to the 4 before? Right there. I'm going to mute for 1 second to cough. There we go. So that should make sense. That should be perfectly normal, right? And the same applies with anything. If we do 2 to the 5 raised to the 7, that becomes 2 to the 5 times 7, right? Dot there, which becomes 2 to the 35. And that's how the power rule works. Now we need to talk about the product rule. The product rule states that a raised to the m times a raised to the n is equal to a to the m plus n. Okay. So let's work out a long one first so we can see this in action. Let's do 2 to the 5. Okay? And let's say that 2 to the 5, that's going to be 2 times 2, 5 times, right? What does this equal? Coughing again, I apologize. I got a little bit of a chest thing going. All right, there we go. I think we're good. Let me get a little drink. All right, what does this equal? Well, we know that 2 to the 4 is 16, but let's just add it up long ways. So 2 times 2 is going to be 4, times 2 is going to be 8, times 2 is going to be 16, times 2 is going to be 32. So we know 2 to the 5 is equal to 32. Now, let's say we're dealing with 2 to the 3. In this form here, we're going to do it like this, times 2 to the 2 is equal to what? 2 to the 3 plus 2. Now let's test this out. Let's take 2 to the 3. That's 2, 3 times, right? So 2 times 2 is 4, times 2 is 8. 8. Let's take 2 to the 2. That's going to be 2, 2 times. 2 times 2 is 4. 8 times 4, what does that equal? That equals 32. So then let's look right here. 2 to the 3 plus 2, what is that? That goes into 2 to the 5. And as we can see just up here, 2 to the 5 is also 32. So you can see that these work, these are true, these are proven to be effective. Now, things are going to get strange moving forward. I'm going to let you know. Because we're going to get into something that's a little bit different here. And we're going to start this off by, I'm going to show you guys something here. Before we go into the next rule, oops, let me just erase that line I drew. Before we go into the next rule, we're going to talk about something. Let's go to our 2's here. All right, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the, actually, you know what? I'm going to give myself a little bit more space here. Let's do it down here. 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. Now we know that these equal, what is 2 by itself? 2 to the 1. Just a 2 by itself, right? We're not multiplying it by anything. So that's going to be 2. 2 to the 2, we said earlier, that's 2 times 2, that's 4. 2 to the 3, it's 2 times 2 times 2. So it's essentially just 4 times 2. 8. These are just going to double each time. If you notice in the pattern, 32. Now, what's 2 to the 0? Let you think about that for a second. Now, let's look at this pattern that we got going here. Let's look at this pattern right here. We notice that every time we have a number, 2 to the 5 is 32. If we divide that by 2, we get the next number, which is 16. We divide that by 2, we get 8. We get the next step up every time. Every time we divide by 2, we get 4. It's the next step up. We divide by 2, we get 1. So what is 2 divided by 2? That reduces to just the number 1. Okay. And that's the case. So let's talk about the 0 exponent rule. And this one's real simply put, it is a to the 0 is equal to 1. For any a, for any a. Any number to the 0 is always going to equal 1. And I challenge you to do this with some other exponents. Try doing it with 5s, 4s, whatever. You'll find that this pattern stays true. Now, let's talk about something that's a little bit more complicated. About 2 to the negative 1, 2 to the negative 2. When we deal with negative exponents, what's going on there? Same pattern. If you follow this same pattern, what is 1 divided by 2? 1 divided by 2 is a fraction. It's 1 over 2. And what's this divided by 2? 1 over 2 divided by 2. Remember when we did our fractions earlier, we said this number floats. Floats up, does magic. That's equivalent to 1 over 2 times 2, which is equivalent to 1 over 4. 1 over 4. Now let's take note of something. Well, first, I guess first let's talk about the rule. Let's talk about the negative exponent rule. That is that a to the negative n is equal to 1 over a to the n. Now, this is very simply put in a sentence that I'm going to offer in a second, but I want to point out something here. When we look at 2 to the 1, we look at this, the value we find is 2. And when we look at 2 to the 2, which is this, the value we find is 4. Notice that when we look at 2 to the negative 1, we see a 2 in the denominator. When we look at 2 to the negative 2, we see the value of 2 to the positive 2 in the denominator. So the simple rule is a negative exponent is a positive exponent in the denominator. And that just makes this much easier to think about and conceptualize. So if I give you 2 to the negative 5, that is equivalent to 1 over 2 to the 5, which is equivalent to 1 over 32. Now, we're going to kind of combine something here. And I want you guys to just imagine this. The same way that if we multiply up here in the product rule, if we multiply a to the m times a to the n, we get a to the m plus n. If we take a quotient rule, whoa, oh, I cannot spell. Come on. Quotient. Spelled. We take the quotient rule, we're saying a to the m over a to the n is equal to a to the m minus n. That should seem pretty evident, though, at this point, because we basically could come to the same conclusion that, think of a way to word this correctly. A to the n in this denominator, okay, is the same. A to the n in this denominator is the same as a to the negative n, right? Because we discussed that up here. We're saying a to the negative n is equivalent to 1 over a to the n. So if we look at a to the m over a to the n here, we can say a to the m over 1 times 1 over a to the n. These ones would cancel and we would be left with what you have above. So this is equivalent. This is equivalent, right? So if we have 1 over a to the n, 1 over a to the n, based on our rule above, the negative exponent rule, right up here, I'm going to put a blue circle around it here. Blue circle. Based on our negative exponent rule, we can know that 1 over a to the n is equivalent to a to the negative n. So then if we rewrite this here, right, And we say that this is a to the m over 1. This time we say instead it's times a to the negative n. We can say that this is equivalent to what? A to the m times a to the negative n. This format here looks very, very similar to our product rule up top. And remember, our product rule, I'm going to put a circle around it again, just to remind you. Our product rule is a to the m times a to the n is equal to a to the m plus n, right? So with that said, we have a to the m times a, so it's going to be equal to a to the m plus, and then here we have a negative n. So it'll be negative n, which comes out to a to the m minus n, which takes us right back up to our quotient rule, a to the m minus n. So those are the rules of exponents, and that's how we're going to be using them. And it's really important moving forward that you guys remember this. I'm going to circle it in red for you because it's extremely important, because once we start playing with fundamental dimensions, this is going to come into play quite often. Okay? This section right here, 1 over a to the n is equal to a to the negative n. Or you can remember it as I wrote it right here. A negative exponent is a positive exponent in the denominator. All right, thank you guys for watching. This is part 1 of lecture 2. We will continue in our ubiquitous units section. Please make sure you like, follow, subscribe, turn on notifications, drop me a comment with your questions, and have a wonderful day.